This is part two of vector equations for matrix algebra. So we're going to continue off. So on this example, we have vector 1, 1, 0, -2, vector 2, -3, 1, 8, and vector y, h, -5, and -3. So for what values of h is vector y in the plane generated by vector v1 and v2? So yeah, so they're asking you for what values of h. So let me write this out. So what they're really asking is for what values of h is vector y in the plane right? So for what values of h is vector y in the plane generated by vector v1 and v2? So we got to find h. That's what we're practically finding. So what I'm going to do is we got to find our linear combination a v1 plus b v2, and then that should give you vector y. So how do we do this? So we're going to write it out as a matrix. So our matrix would be expressed as 1, 0, -2, right? And then -3, 1, 8, -3, 1, 8, and then straight line because we need that equal sign. And then it's going to equal to h, -5, and -3. Okay, so what we have to do is we want to get everything on this 0. We want this 8 to be 0, right? We want this to be 8 to be 0, and then we want to make this -3 to 0, and hopefully we can find our h. So what I would do first as a row of operation is maybe make this -2 into a 0. And how would I do that? So -2 is technically in row 3. That means we're only messing with row 3. And to make this -2 into 0, you're going to multiply 2 times row 1 plus row 3. That will give us your new row 3, right? So that would be expressed as 2 times, what's my first number in row 1? 1, plus my first number in row 3 is -2. So that gives you 0. So you put 0 here and continue the process. So 2 times second number in row 1 is -3, plus second number in row 3 is 8. So that would be 2 times -3 is -6, plus 8 is 2. And then straight line. Continue the process. 2 times. Okay, so our third number in row 3 is actually not a number, it's a letter h. Plus my third number in row 3 is -3. So that would be 2h minus 3, right? Now don't be discouraged. Keep on putting. We're trying to put it in row echelon form. So keep on going. So this would be 0, 1. This is -5, and then this is 1, -3, and h. Okay. Then what I would do next is let's try to make this. So this already has a diagonal one, so that's good. Now let's make this 2 into a 0. So how would I do that? So this 2 is technically in row 3. We're only going to mess with row 3. And to make this 2 into a 0, I would have to multiply -2 times row 2 plus row 3. And then that will give us your new row 3. Right, so it's going to be -2. Now we're using this matrix. -2, first number in row 2 is 0, plus first number in row 3 is 0, so that would be 0. And then continue the process, -2. Second number in row 2 is 1, plus second number in row 3 is 2. That's 0. And then keep on going, -2. And then first number in row 2 is -5, right? And then for last number in row 3 is this whole thing, 2h minus 3. So -2 and -5 is 10 plus 2h minus 3. So that's 2h. And then 10 minus 3 is 7. So that would be 2h plus 7. Okay, and then this would be 0, 1, -5. And then this is 1, -3, and h. Okay, so we could stop here. The reason why we could stop here is because this is, you don't want to have this situation. 0 does not equal to 2h plus 7, right? So that's a big no. So unless we can get 2h plus 7 equals to 0. So basically, we're trying to solve for h, right? Unless, so this statement is false unless we say 0 equals to 2h plus 7. Right? And then if you solve for h, so I would subtract 7, this is -7 equals to 2h. Divide this by 2, divide this by 2. I get h equals to -7/2. Okay, so yeah, so the if h does equal to -7/2, then y is in the plane. Okay, so yeah, that would be the answer for this one. So if h equals -7/2, then y is in the plane. Let's move on. Let's deal with existence and uniqueness questions. So on this example, let's say matrix A is equal to that, and matrix or vector B is equal to that. And let W be the set of all linear combination of the column of A. Part A says, is vector V in W? So we have, so this column could be A1, A2, and A3. So we got to find the linear combination or the coefficients. So we got to do C1, A1 plus C2, A2 plus C3, A3, and then does that give you vector W? So we have to find the coefficients. And then that gives us your weights. So what we're trying to do is, can you come up with B1, A1, C2, okay. So C1, A1, C2, A2, C3, A3, vector V. So how we would set this up is you don't know the coefficient for C1, and then A1 is the column to -1 and 1. And then C2 is 0, 8, -2. And C3 is 6, 5, 1. And then does that give you vector 10, 3, 3, vector V? Okay. So we're going to have to do some, so we're going to do some robots. So now, how do we do this? We use matrices, right? So we're going to set it up as uh, 2, -1, 1, 0, 8, -2, 6, 5, 1, and then it's 10, 3, 3. So we want it in row echelon form, right? We want the diagonals to be ones, and we want everything under column 1 to be zeros. So what would I do first? Let's make this -1 into a 0, right? So how would I do that? So that's row 2. To make this -1 to 0, you're going to have to multiply, you're going to do row 1 plus 2 times row 2, right? And when you do that, you're going to get 0, 16, 16 straight line, and then this is 16. We didn't mess with row 1, so it's going to be 2, 0, 6, 10, and then this would be 1, -2, 1, and 3. Okay, and then what we're going to do next is make this 1 into a 0. So that's going to be in row 3. And to do so, you're going to do -1 times row 1 plus 2 times row 2. And that'll give us your new row 3. So that when you do all the work, you get 0, -4, -4, and -4. And then row 2 stays the same, row 1 stays the same. So this is going to be 0, 16, 16, 16. This is going to be 2, 0, 6, and 10. Okay, and then I would do is, let's see, let's make these 16s ones, and then let's make these -4s ones, because I think it'll be a lot easier. So maybe to make these 16s into 1, you're going to have to multiply it by the reciprocal, so that would be 116. right? And then to make these -4s into 1s, maybe you can multiply it by 1/4. We can do we can multiply a scalar more than once, and then maybe we can make these 2's. Let's make this 2 into 1 by multiplying it by the scalar 1/2. Okay, so when you do that, you're going to get this new matrix. It would be This would be 1, 0. This is a 6, so this would be 3, and then this is 5. This would be 0, 1, 1, 1, and then this would be 0, -1, -1, and -1. Okay. Now what I would do next is, yeah, that's much easier. Now I would make this -1 into a 0. And how would I do that? By adding row 2 and row 3. So this -1 is technically in row 3, so you're going to say row 3. And then you just add row 2 plus row 3. And then that will give us your new row 3. So this would be 0. 1 plus -1 is 0. 1 plus -1 is 0. Straight line. And then 1 plus -1 is 0. And then this would be 0, 1, 1, 1, 1, 0, 3, and 5. Then what I would do next is now, okay, so now we have a true statement. Remember, so this is column x1, x2, x3. This is like saying 0x3 equals to 0, which is true, right? 0x3 or 0 equals 0, that's a true statement. So that means it is consistent. And what that means, it really means it's infinite solutions. So infinite solution. So you have more than one solutions, right? So if you go back to the question, part A says, is vector B in W? Yes, because this just proves that you have many solutions. So you could say big yes. Okay, let's do part B. Part B says, show that the column of A, show that the third column of A. So third column, so what they're doing is now, the third column is A3. So what you're doing is, if you go back to this matrix, you're gonna make this equal to the last statement. So you're gonna replace 10, 3, 3 with 6, 5, 1. And now this is gonna be, so you're gonna set it up like this. So what they're saying is, you're gonna set it up like this. So it's gonna be 2, -1, 1. So what happens is this stays the same, and this stays the same. Almost like Cramer's rules, and then straight line equals. Then what you're going to do is replace 10, 3, 3, 10, 3, 3 with this vector 6, 5, 1. And then we're going to do row of operations. So we're trying to get all our diagonals ones, and then everything below zeros. So let's see. What I would do is make this -1 into a 0. So that's this -1 is technically row 2. So to make that into a 0, you're going to do row 1 plus 2 times row 2. So this would be 2 plus 2 times -1, which is 0. And then it's going to be 0 plus 2 times 8, which is 16, straight line. And then it's going to be first number in row 1 is 6, plus 2 times row 2. Third number in row 2 is 5. That would be 16. And then this would be 2, 0, 6. And then what I would do next is get this 1 into a 0. So how would I do that is maybe do row 1 minus 2 times row 3. Yeah, so I'll do row 1 minus 2 times row 3. And then that'll give us your new row 3, right? So that would give you, I'm going to just do the, I already did the work, so, but this gives you 0, 4, and then 4, and then the top column, row 2 doesn't, row 2 hasn't changed, so it's 0, 16, 16, and then this would be 2, 0, 6. What would I do next is make this 4 into a 0. So how do I make this 4 into a 0? Maybe do row 2 minus 2 times row 3. Yes. So to make this 4 into 0, I'm going to do, actually, no, it would be 4 times row 3, sorry. So it would be row 1 minus 4 times row 3, right? So this would be 0, this would be 0, and then this would also be 0. And then this is 0, 16, 16, and then this would be 2, 0, 6. Now you could stop here, 206. The reason why you could stop here is because this is true. This statement is true. 0 does equal to 0. And yeah, 0 does equal to 0. So it's still yes. So it's going to be yes, it's still consistent. Okay. Okay, let's talk about more existence and unique questions. So on the next example, so on this example, can any vector in R2 be written as a linear combination of part A vector 1, 3, and 2, 5? So what does that really mean is 1, 3 could be expressed as vector 1, and then 2, 5 could be expressed as V2, right? So does vector 1 comma vector 2 give you vector 1? So vector 1 is 1 comma 3, and vector 2 is 2 comma 5, right? So what this really means is does A V1 plus B V2, does it span R2 or two pivots? What about does it span R3 or three pivots? So if we do this, it would be 1, 3, 2, 5. And then does that equal to, so let's try to put this, let's make these 0. So to make this 3 into 0, or how about let's make this 2 to 0, so you would have to multiply 5 times row 1, 5 times row 1 minus 2 times row 2, and that would give you 1, 0, 1, 1, right? And yes, that gives you a pivot in every row. Right, so let me make so it's 5 times row 1 minus 2 times row 2. And that gives us row 1. Five minus 2 times 3 is -6. It's -1, and then 5 times row 1, 2 times. That's 10 minus 10, that's 0. Oops. Yeah, and then this is 3, 5. So basically, and then multiply this by 1/5, you'll eventually get to here. But the point is, there is a pivot in every row. So yes, the answer would be yes, because v1 and v2 are not scalar multiples. Yes, since v1 and v2 are not scalar multiples, we get a pivot in every row. Okay, so yes. Yeah. So what about part B? We have vectors 1, 3, and 2, 6. So what we're going to do is try to set it up like this. A v1 plus B v2 equals to B. So will I get two pivots? So this would be 1, 3, 2, 6. And let's try to make this 3 into a 0. So how I would do this is multiply -3 times row 1 plus row 2. And then that would give us your new row 2. So when you do that, this row would be 0, 0. And then this is 1, 2. So you only have one pivot. This is one of your pivots. So we need two pivots, so no. You only have only one pivot, right? This one is your one of your pivots, but we need two pivots. So no, it does not work. It does not work. So basically, the span is all linear combination, but in grouping of vectors, we don't want any combination. We don't want to take the original vectors and combine them to make more vectors. I mean, what we really want is we want to take the original vectors and combine them to make more vectors. That's our goal. We don't want the vectors that we are starting with to be alike, right? They can't be scalars, that's what I mean. So we want to take new vectors and come up with new vectors. Uh, you could think of it as walking and swimming. They are two different things, but it gives you the world, right? So let me write this down. Let me write this down. So the span is all the linear combination. But in grouping of vectors, we don't want any combination. We want to take the original vectors, and combine them to make more vectors. We don't want the vectors, we don't want the vectors. We don't want the vectors we are starting with be all alike. So what that really means is if you look, uh, we're trying to find the constants, right? We're trying to find this is a linear combination, this is a linear combination. This means that A equals to B. These linear combinations are the same, or also known as scalar. The scalars are the same. That means that's why this does not work. Uh, in linear algebra, we want is what we really want is we want to take new vectors and come up with new vectors or new linear combinations and come up with new vectors. Think you could think of it. Think of walking and swimming. They're two different things, and it gives you the world. But running and walking are almost the same. So what if you want to do running and walking? Uh, that work. I mean, this works. Walking and swimming, they're two different things, but they still give you the world. But what about running and walking, right? They're almost the same thing. Some people's walking is the same thing as other people's running. So they're almost the same thing. They both give you the world, or if you want to travel to the UK, that's fine. But do you really need both of them? So the question is, do you really need both of them? They're almost the same thing. Uh, do you really need both of them? So that's why that doesn't work. Do you really need? No, running is a scalar multiple of walking. So no, running is a scalar. Okay, so I think that is the last. Yeah, that's the last example for this one. So this is linear combination and expanding. I will stop here.